laser range finding is one approach, but if you look, by the way, if you look at another application of 3D, this is in a form is 3D imaging, right? Because you're trying to get shape recognition of the environment around you. Another important application is self-driving cars. So if you look at what the Google self-driving car does, that does something like this. Basically, it uses something called a LiDAR, right? That you might have heard of, which is essentially light-based detection and ranging. So that's exactly what we just talked about, but in a slightly more complicated setup where the LiDAR system itself is spinning. This is, for instance, what the Google autonomous car uses. However, the Tesla famously does not use any of this. It uses cameras. And it's a philosophical difference. Of course, cameras are cheaper, but the software and the algorithms you need to be able to do the shape recognition is a bit more complicated. The LiDAR is more expensive. So this is the key difference, but there's an engineering trade-off between these two, right? So again, from the perspective of your project teams, this might be something of interest that you might want to take a look at. So how would Tesla does it? They typically use stereo vision system. So the idea would be to combine two cameras. It can be more than two as well. So in the case of the Tesla, I believe they have something like 16 cameras because you have to look at the full 360-degree field of view. Of course, the cars use not only cameras, they also use other things like ultrasound detectors and so on. For long range, it uses radar as well. I'm just talking about the relatively short range shape detection. And in this case, you essentially apply the data from multiple cameras and then image processing for fast, accurate shape recognition. Of course, we all know this works. This works naturally for all of us. Because we have two eyes, we have a perception of shape, right? Because if the object is close by versus object is far away, because you have two eyes, you're seeing two different perceptions. But your brain actually puts them together to create the full three-dimensional view, right? Each of your eyes is seeing only a two-dimensional view, right? Because your retina is two-dimensional, it's a surface. But because you have two retina and your brain is a pretty fancy machine learning or human learning machine, let's call it, it can put together the full three-dimensional view, right? So you can see this full 3D picture. And of course, you can create a perception of this in full 3D displays and so on, which is what's shown here. You present one image to one eye, another image to the other eye, and the brain essentially fuses them together to give you the full 3D picture. In old 3D movies, if you go to the movie theater, you remember putting on glasses where you have, one polarization through one eye and another polarization through the other eye. That's a very common way to do these sorts of things. You can imagine, and that's for displays and perception, of course. But in the case of shape measurements, we can't do that. We have to apply the image processing algorithms. So those are some examples of where optics is applied. Now, as I said before, the other aspect of this whole resources recycling market is the market driven and more importantly policy driven, because there are many different versions of recycling markets, right? You can have single-use versus multi-use containers. We are familiar. The multi-use containers would be plastic bottles that are reused again and again, single-use aluminum cans that are simply destroyed and remade into something else. As I said before, there is the issue of container deposit. Not all states have container deposits. They're state laws, so different states have them. So, for instance, in Massachusetts, it's like something like 5 cents for an aluminum coin, and not everybody actually participates. So, for example, if I buy a can of Coke, I have to pay an extra 5 cents. And if I'm too lazy to return that can and get my 5 cents back, that means that 5 cents that I paid when I purchased the can remains in the system, right? I never reclaimed it. So this would be what's called a non-participant. And the non-participants, because I'm lazy to return my can, I essentially pay for the equipment. And that turns out to be a pretty significant amount of money. So for instance, we have 90% participation, there's 10% of deposits that are never claimed, and essentially finances the infrastructure and operation. So it's kind of a nice irony to it to some extent. Of course, the vast majority of markets are non-deposit. So in Utah, of course, we don't have deposits. And in this case, the commodity prices drive this industry. So, and then what's really important is, how can we sort these materials into as pure materials as possible? So if you can get, 99.99% of copper, then you can, claim a very, very high price, as opposed to if it's a 90% copper, right? So because then someone else has to do the sorting. So that difference might make a big difference into how the recycling infrastructure is actually implemented. So if you actually read that KSL article, it actually goes into at least briefly into some of these discussions. So it's worth taking a quick look. Of course, not only so the accuracy of sorting is of course very important because of the pricing you can command. But of course, efficient transportation is also important because you are talking about actual real things, and you need to be able to ship them different places. That tends to be an important cost driver as well. Something to think about, as well as storage, right? Storage, as we talked about before, is also critical, especially in the case of the reverse vending machines. So all of these factors have to also be taken into account when we think about technology, even from the optics perspective. Now, we know that there are all kinds of materials in recycling. The most expensive ones are copper and various kinds of metals, right? Gold, palladium, and things like that, used in electronics and things like that. Now, those require very complex forms of sorting and recycling. Some very simple, like magnetics, right? So if you have ferrous materials, irons, and certain kinds of alloys of copper, you can actually separate them out with magnetic strong magnets and robotics. However, and in some cases, people use X-ray fluorescence spectroscopy and things like that. We won't talk too much about it. But on the other hand, recycling plastics is quite challenging because all the different plastics look alike, right? They're all transparent, essentially. However, all these different kinds of plastics, this is polycarbonate, polyethylene phthalate, polyethylene, polyvinyl chloride, and all these different things are different, right? And they command different prices in the market. So in order to be able to sell them, you need to be able to identify them and sort them out. And that turns out to be a very challenging problem. And one of the important solutions to this problem is something called near-infrared spectroscopy. This is actually a very simple idea. Think about it this way. Imagine you have a beam of light, okay, and you have a piece of plastic. Now, we know from the law of that what we have learned in the first half of the semester, part of the light is reflected, right? That's the law of reflection. I'm just drawing it at 0 degree incidence angle. It doesn't have to be. Part of the light, of course, is refracted and comes out, right? That is following the Snell's law and so on. But as you recall, if I have two parallel lines, I'm going to draw this more accurately since we should know how to do this, right? This will follow Snell's law. So this input light is essentially parallel to the output light. So if I come in normally incident, I'm going to come out normally out incident. Out, right? So what is interesting is that different plastics essentially transmit light differently. So if I look at the transmission at one wavelength, λ1, versus another wavelength, λ2, different plastics will have different transmission. And that's what's plotted in this chart here. So on the horizontal axis, I have wavelength in microns. So you will notice this is going from 1.5 to 2 microns. So this is the infrared, or it's also called the telecom wavelengths. Telecom or the K band, there's all kinds of names for it. It's about 1.55 microns, roughly. And you might also notice that these wavelengths are invisible to the human eye, but it turns out that some plastics will absorb it. And on the vertical axis, I have transmission. So that's what I meant here. Transmission is simply the power output divided by the power input. So I measure the power going in, and this transmission is simply P out divided by P in as a function of wavelength. So pretty simple, right? All I need to know is I need to know how much power I send in. Let's say I send in 100 watts. And I have a detector here which measures, oh, okay, I measured 9 watts. So I know my power out by power in is 9 or 9%, right? And you can plot it that way. So that's what you get as a function of wavelength. You see these plots. Now, if you look at these plots, what you notice is that different colors represent different plastics, and different plastics have different signatures. This is called a signature. More accurately, this is called a spectral signature. In other words, different plastics will have different absorption spectra. And by measuring this very quickly, cheaply, fast, accurately, I can actually identify what kind of plastic it is. Now, by the way, I can also do this for glasses, right? Glasses are easier because there's not that many different kinds, and you don't need to sort the very different. I mean, glasses are generally easier to sort because you only look at the quality of the clarity of the glasses. Sorry. In the case of plastics, it's a little more complicated. But of course, you should also keep in mind, plastics also have different clarities, right? Some plastics are very clear, like plexiglass, but some plastics might not be so clear. So you also have to account for that. So those turns out to be a complicated problem as well. So essentially, this idea is what's called near infrared spectroscopy. So it turns out to be a very important optical technique. And now you know what that means. Now, there are various ways to do this. Like I said before, you need some sort of light source, right? You need a light source which has all those wavelengths. A good example of such a light source is a mercury arc lamp. So this is relatively cheap. It uses a lot of power, but it's inexpensive. LEDs, you can have infrared LEDs today, which are better sources, relatively cheap also. The other side, what you need is a detector, right? You need a detector. Now, it turns out the cheapest detectors you can buy today are things like silicon, right? What you use in your cell phone cameras. Those are really cheap. However, silicon has a band gap of about corresponding to about 1.1 microns. So that means that these long wavelengths are not absorbed by silicon, unfortunately. So in other words, these wavelengths will pass straight through silicon. Silicon is not a good detector. So that turns out to be a hard problem. You have to use materials like indium gallium arsenide and things like that, which have a lower band gap. So it can absorb these wavelengths. By the way, the reason why you have to use these long wavelengths is because, as you see here, the transmission into the shorter wavelengths is very high. You don't see a spectral signature at those wavelengths. All plastics are essentially transparent in the visible, right? They pass through, most of them anyway. So you can't really distinguish them easily. Otherwise, you would just use a regular camera. So it turns out this turns out to be very expensive. So that's one kind of a fundamental problem. Nevertheless, these techniques are relatively common. And I'll talk about one very interesting innovation that this company Tomra came up with, which was to use a technique called correlation spectroscopy, which is relatively inexpensive and simple. In this case, they used a halogen lamp at the source, an in-gas detector as the detector, which is expensive, of course, but you can't get around that. But instead of having a very one thing I forgot to mention, if I go back here, one problem that I forgot to talk about is, of course, with a laser, a source and a detector and the plastic in between, I can measure P out and I can measure P in, right? Those things are known. However, how do I change the wavelength? Now, I need a source that's tunable. This turns out to be not so easy. Tunable wavelength source. This turns out to be expensive. So you want to avoid this somehow. That was their innovation. That was the problem they were trying to solve. So how did they solve it? They essentially used a broadband source, which is this halogen lamp here, and then an in-gas detector, exactly as I showed before. So you have a source, you have your detector on one side, and then you have your plastic here. Now, what they did was cool, was that they introduced a filter here, a filter wheel. Okay. And this was the very simple idea. This filter wheel has many quadrants, as you can see here in this picture, right? That's the filter wheel. And each of these little slices has different kinds of plastic that you're trying to find. It doesn't have to be what you're trying to find. It can be compensated in the mathematics of this once you capture the signals. But essentially, you have different kinds of plastic here, different color filter here, and so on, right? And this whole thing simply spins. And as you spin in your detector, what you see is a variety of signals. So this is time. What you see, this is your signal on the detector, simply goes up and down, right? You get all kinds of weird things. And the signature, this time signature of this now corresponds to a particular kind of plastic, let's say PET. And by calibrating different plastics, and of course, nowadays applying machine learning with all kinds of data, you can get a very robust reading of what kind of plastic it is. Oops, sorry. Go back here. Yeah, so the idea is that it's a relatively inexpensive approach because all you need is a cheap source, the halogen source. The detector is expensive. This is very cheap plastic, and this filter. This plastic is simply what you're measuring. The filter wheel is cheap. Just it's a 3D printed part or machine injector molded pulp with a bunch of plastic, right? And then of course there's software behind it. But very cool idea, works really well, and you can identify and sort things really, really fast. It's a very simple innovation, something to think about. Here's an example of a machine that they actually implemented this technology on. Of course, that's the name of the company. This is where the bottles go in. Now, a second innovation that they talk about in that article is actually even cooler and is related to some work in my lab. So I want to just quickly highlight this. They used instead of that filter wheel with the plastic sources, pieces of plastic. By the way, one of the problems with this approach is that you only have a few of these, right? There's 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. So you can only really get 12 or 15 or so signal values. What if you want a lot more, or you want a more better control over the spectral measurements, essentially? In that case, you want to use something a bit more accurate, and in their innovation was to use something called a diffractive optical element. And we won't talk too much about it, but in the electron spectrum splitting, I'll come back to this idea. But this was their idea to make a very low-cost spectrometry. This device here, this is what it is essentially made similar to a CD or a DVD. You make a master, and then you stamp them out, so it can be extremely cheap, like pennies. And what it does is that it takes the light from a source, which is shown here, and when it's a reflected device, similar to a CD, the light bounces off this DOE and it disperses, it diffracts. So different colors will disperse as shown here. It forms a rainbow in the vertical direction. Okay, so that's one. So it creates this spread of wavelengths, but then they actually vibrate this DOE in this axis. Okay, and it's moving mechanically in some resonant motion, really fast. Now, what that does, it moves this the signal in this axis shown here by those black arrows. Now, this DOE is a two-dimensional DOE, so it spreads the wavelength in this, but also creates these different bands, as you can see. And you see those different bands are shifted up and down slightly. Now, what that does is, if you have a single detector, remember the detector is expensive, so they're trying to make a single pixel detector. By moving this pattern movement, this detector over time captures different portions of the spectrum. And this can be done very, very precisely. And you can do this very with high signal to noise ratio, because this DOE can also do some focusing. It's like concentrating the light from the source as well. So you can get high SNR as well. So this leads to high SNR. And then applying some signal processing, you can actually extract the spectrum out of this. And I'll talk a little more about it in the second half of today's lecture. Now, the last point to keep in mind here is that, of course, once the recyclables are collected from a home, they actually have to be processed in some central facility. And in that, this is something called it's usually done at a municipal scale or a city scale. So in the KSL article, they talk about the Salt Lake City implementation. And this is very large scale material sorting. And we're talking about, 30 tons of waste per hour, maybe 10 times that for some large, New York or Los Angeles, something like that. And the idea here is that, of course, you don't want all of that to go into the landfill because that's unsustainable. And it's a huge waste of resources, right? You basically are throwing away things that can actually be recycled. It could contain valuable materials. Of course, metals and so on are pretty important. However, this has to be done really, really fast. So it's very large scale, high throughput sorting. This turns out to be really very challenging problem. And in this case, typically you use both near infrared spectroscopy, but also visible spectroscopy. And it's captured a very, very high spatial resolution, typically at a few centimeters, but it goes extremely fast. So these conveyor belts are going at several tens of meters per second sometimes. Now, of course, the reason to do this is material costs, as I've said before. I won't dwell too much on it because these are old numbers, but you can imagine, what the aluminum costs or PET costs are. So what does one of these systems look like? This is an example of a huge machine where you have these conveyor belt, essentially the materials coming through, and materials are being identified, and the robotics which essentially pick and place these materials very, very quickly. By the way, I'll come back to other applications at the end as well. If I zoom in here, you can get a picture for exactly what's happening. So here you see the materials are coming down here, going this way on the conveyor belt, and there's a scanner here, which essentially in this example they're doing a oblique incidence from the sides, and the reflected light is captured with a high resolution camera, and there's probably spectroscopy here as well. So it's also spectral imaging. In fact, I will talk about this later on. Now, of course, this then identifies the materials and sorts them. And here you can see a air jet coming in and blowing the bottle into this container, whereas the other materials fall into this container. So it's a very simple example of a two-class sorting. And of course, all of this air jet is controlled by a machine learning algorithm, which is fed by the spectral imager, right? So that's how it works. And of course, lots of innovations happening here because this has to happen really, really fast. It's not only just 2 things that you're sorting, you might have 10 things you need to sort. So it's a really complex problem. People are still improving all the time. Okay, and you can imagine there's all kinds of applications. So I want to end this part of the lecture with 2 very short videos. One example is a video from a team that used this problem as part of a project team about 3 or 4 years ago. I can't remember exactly. And they came up with what I thought was a very cool idea. That's why I want to highlight it. So I'm going to play it, and then we can chat briefly, discuss if there are any questions about it briefly. By the way, this is an example of it's a good video that I expect you. By the way, I forgot to mention, but at the very final assignment, you have to produce a very short video, kind of like this. This is 5 minutes long, which is a little bit long in my opinion. It should be a little bit shorter, but I'm going to play this first and we can talk briefly. There are questions.
Distributed Plastics LLC would like to introduce you to a distributed plastic sorting method by simply reading the SPI resin code on consumer plastic waste. Distributed Plastics LLC is backed by Bing Shen, a PhD candidate, and Joseph Bogue, a master's degree student, both at the University of Utah's Electrical and Computer Engineering departments. Currently, consumer recycling is done in a big box manner, whereby large trucks go from house to house picking up recyclables. They then take these recyclables back to the plant where they have to sort them, compact them, and bale them for sale. Although this big box sorting method is proven day after day, These sorters are expensive because of advanced methods of discrimination. These sorters use visual and infrared wavelengths, spectroscopy methods where actual elemental makeup is determined, X-ray imaging for difficult materials, and lastly, the human element for anything that might have been missed. Although these big box sorters are marvelous feats of engineering, they come at a large monetary cost, both initially and through time. Now, in a recent case study done in Salt Lake Municipal's Recycling Center, they recently made a $7 million sorting capability upgrade. This upgrade is a great improvement for them. However, if recycling in general is done in a distributed manner instead, these types of costs can be greatly reduced. Now, before we get into the innovative technology, we need to review plastic resin. Remember that plastic is a synthetic material made from a wide range of organic polymers like polyethylene, PVC, and nylon. These polymers can be molded into virtually any shape and are easy to recycle if kept in the same resin family. This is why it is important. Keeping these polymers together allows for efficient recycling and more dollar per bale. Notice the code, the SPI resin code on this plastic bottle. Now, simply put, our innovative idea is a smart garbage can. This smart garbage can will take your plastic bottle, find and read the SPI code, and drop it into the appropriate internal compartment. It is centered around consumer plastic bottle waste and will automatically sort it as you walk away. It has 8 columnar sections, 1 for each SPI code and 1 as overflow, with a center hollow section that will contain smart electronics. Above this center columnar section is a domed top with an enclosure that holds the plastic bottle on an incline. When the bottle is dropped in, the algorithm reads the SPI code from the image, determines which bin to rotate towards, and opens a door and lets gravity take over to do the sorting. Notice here in the prototype overview, a high-resolution camera sends an image to MATLAB. The patentable detection algorithm then decodes the SPI code and sends that value out via serial data to a microcontroller. The microcontroller then drives a stepper motor and actuates a door to open, dropping the bottle and sorting. Actual prototype results show a noise-induced, hand-drawn images sent to MATLAB. MATLAB detection algorithm successfully detecting the SPI code and sending that data via serial to a microcontroller. The microcontroller then correctly drives a stepper motor to the correct SPI code location, and a LED will blink showing or simulating that a door has opened. Now,
so in that example, they actually built a very simple
Salt Lake
prototype.
County, conservatively, has a potential for a 30% increase in volume and a 3x decrease in cost if using a distributed plastic sorting method. The nitty-gritty of this claim follows. Salt Lake Municipal per week has a conservative capacity of 336,000 kilograms per week. Another conservative estimate of our distributed methods shows 431,000 kilograms per week. That is a third volume. Another conservative estimate over 30 years shows our distributed method costing $22 million, whereby the large big box sorters have a infrastructure, maintenance, and overhead cost of $70.5 million. Again, this reflects our claim as a 3x reduction in cost. Remember, at Distributed Plastics LLC, we thank you for your consideration.
Okay, great. So this is an example of a very, very nice presentation. There are three aspects I really like about it, and something to keep in mind when you actually make your final, as you work in your project. First, it's a very simple idea, right? So it's a relatively simple idea, easy to understand, and so on. Second, they actually prototyped it, and they didn't build the entire thing, but they built a little microcontroller, a little software, and they showed that it actually selects an arrow moves, kind of indicating the identification and sorting of the bottle. And lastly, they did a very simple kind of market analysis and a payback template. So I would expect you to actually do something similar at the end of this class. So keep that in mind as you work on things. Now, the last video I want to show before I move on to another topic is just to emphasize that optical sorting is, of course, not used only for resource recycling. There's a huge amount of other applications as well. And I just wanted you to appreciate one of them, which is actually quite important. Of course, we talked about the self-driving cars and things like that, but let me just play this quickly. And then I'll probably talk over it. Oops, it's loud. So here they're sorting grapes. And it's really amazing to see what happens. I just wanted you to kind of appreciate the scale here. This is a German company, so that's where that is. Of course, very important for vineyards and wineries and so on. Sorry, I should turn off the music, it's too loud. So there's a pre-selection, this is important. You don't want the raisins going into your wine. Yes. So you can see it kind of separates it out, but the sorter is going super fast. But there's this portion here, just kind of separating them out, reducing clumping and things like that. Now, this is way too fast, but they will slow it down so you can see what's happening. There you go. So here there's a very high-speed camera and detection algorithms that is essentially using pneumatic injectors, the air jets, as I showed before, simply to push away the debris. And obviously, it's going extremely fast. This is 16 times slowed down. So this means that all your computation and the feedback to the robotics has to happen, at least twice as fast as that, right? To meet Nyquist. And there's the rejected particles. And the good grapes are sorted out. Very simple example. Important example. I guess not so perfect. I see some stems and stuff. Okay, great. So you can imagine the same sort of thing is important for other agricultural products like avocados, strawberries, blackberries, whatever, right? Nuts. The nuts actually a very important part.